Okay, so we're recording and picking up from where we left off last time. We were talking about change of variables. We did several examples. What I didn't do, because there was already so much going on and so many things to be confused about and plenty to have to worry about, I didn't ever demonstrate, give you any motivation for why it is that my claim about the stretching factor formula being this right here, I never gave any justification for why that is. Right? So that's what I want to talk about now just a little bit. I think it's good for you to at least see approximately how this argument goes. Anyway, here we go. So the big idea is that the little image parallelogram of a little piece of differential area over here, right? So we have an input piece of area and then a resulting output piece of area. Again, these are the teeny tiny, right? The little itty bitties, the differential sizes. The area is stretched by some factor. Now you can see that we're going to get the result we want. We're literally viewing the blue area as being, as a result of this computation, a factor times the green area. Right? We're going to get the right answer. The question is how to make that argument. And there's a couple steps in the process. The first step is to realize that this parallelogram, we have a formula for how to compute the area of a parallelogram in R2. Oh, whoops, wrong color. It is the absolute value of the determinant of the matrix that you get by looking at the edge vectors as the columns. Right? So now what I need to demonstrate, I need to persuade you that these are in fact the formulas for these edge vectors. Okay, how do I know that these are the right formulas for those edge vectors? Well, I'm going to claim and then argue that those edge vectors are the images of these edge vectors here. Now these edge vectors on the left are pretty easy to understand. I mean, we know this is a little rectangle that's width is du, which of course is horizontal, so E1 du, and the height is dv. Of course, it's vertical, so that's E2 dv. So how do I turn input vectors into output vectors, keeping in mind that vectors represent changes? So let's say it again. How do I turn input changes into output changes? Well, I turn input changes into output changes by multiplying by the derivative matrix, right? This dg right there. dg, the derivative matrix, is what turns input vectors into output vectors. And thus we have that this and that are the formulas for those, what we've already argued, need to be columns in that matrix. Okay. Now, the rest of this argument, I'm going to let y'all read through. This is straight up linear algebra from this point. You just need to persuade yourself, for one thing, that these two scalar factors, du and dv, will factor out. So think about the properties of determinant and how that works with constants in columns and all that business, just linear algebra. And then you also need to persuade yourself, and again, this is a good exercise in linear algebra, that this matrix here is in fact just a DG matrix. And the trick there is going to be to think about, well, what are these columns, right? The first column of what I have here is DG times E1. Think about, what is that? And you can write down exactly what that is. And then likewise, what is this second column? And when you get this all written down, you will find it is exactly DG. So that's how the argument works. It's the broad brushstrokes anyway. And as desired, the stretching factor is what we had previously claimed. Okay, moving along. Let's talk about three-dimensional change of variables. Here's the good news. It's almost exactly the same as two-dimensional. It's as similar as it could possibly be. So it remains that if you have an undesirable domain, such as this nightmare right here, right? If you have an undesirable domain, and if you can make that an image of a better, more desirable domain, such as, a nice little rectangular box, everybody's favorite, right? Then you can do a pullback by plugging in. Again, it's just a matter of plugging in. And then, of course, you have to recognize that there's a stretching factor, and it will again be the case that that stretching factor is the absolute value of the Jacobian determinant, just like in 2 dimensions. So it's still a pullback in the usual way, and the stretching factor is still computed by the same formula. Now, I'm going to suggest this as an exercise that persuade yourself that this is, in fact, the correct formula for that 3-dimensional stretching factor. Here's how you're going to do it. You're going to shamelessly steal from what we just argued right here. It's practically exactly the same. Not quite, but really close to exactly the same. The only adaptation you have to do is, of course, to imagine that this is no longer a 2-dimensional rectangle, but a 3-dimensional rectangular box. Its image, of course, will then no longer be a parallelogram, but the image will be a 3-dimensional parallelepiped, which again is going to be understood by edge vectors, which again will be computed with the derivative matrix, and everything else is going to follow through in surprisingly similar ways. So again, think about how you'll take the argument that we've already done in 2 dimensions and adapt to make it 3-dimensional, and you will get, again, morally the same answer as we're claiming over here. Okay. Now we're going to put that into practice. Before I do this next example, I do need to talk about this theorem right here. This is kind of a corollary for, a lemma for what we're about to do in this next example. It's just a shortcut. Here it is. Neat fact: if you have a matrix, if you use that matrix to define a linear transformation in the usual way, and if you take that linear transformation and compute the derivative matrix for the linear transformation, you will get exactly the original matrix. This is very straightforward to check. I'm going to suggest you do it, for example, in, let's say, just in 2 dimensions. Not that it's the same in any dimension. But write down an arbitrary 2x2 matrix, ABCD. Multiply this out to get a formula for your linear transformation. Take the appropriate partials to write down the derivative matrix. You're going to get exactly ABCD. So, anyway, it's a little 3-minute exercise, 2-minute exercise, something like that. Take the time. Persuade yourself that this is a true statement. Feel free, as always, with these suggested exercises, come talk to me in office hours. I'll be very happy to help. But give it a try. Okay, so with that established, we're going to move on now and do a 3-dimensional change of variables, pulling back through a cleverly chosen change of variables function. Okay, here's the question. Compute a certain triple integral given a domain that is this parallelepiped right here. Now, before we do this the clever way and invoke change of variables, let's just recognize, just so we can appreciate the benefits of what we're about to enjoy, how ugly would this be if I had to slice up this solid, the old-fashioned way. If I had to, start taking slices perpendicular to the y-axis, for example. Okay, well, oh man, you're going to start at that corner. You would end at that corner. There are a total of 8 corners. That means the remaining 6 corners are going to be in the middle of the calculation. That means you're going to have 7 integrals. So already, I think we're hopefully persuaded that this is a hard problem. But it gets worse, because depending on the value of y and where you're looking, and this is artistically very tricky, so I'm going to make an effort at this, and it's going to be poor, and I apologize in advance. But let me try to draw one of those y slices. kind of one of the ones in the middle. The y slice might look something kind of like, I don't know, something kind of like that. That's terrible, of course. But the point is, depending on where you are, right, the y slice through a parallelepiped is not always going to be a triangle. It's not always going to be a parallelogram. Sometimes it's a hexagon. It's weird, right? So this is not just 7 integrals. This is 7 categories of y slices, each one of which is going to require several integrals on its own. This is not 7 integrals. This is like 20 or 30 integrals. This is a nightmare of inconvenience. Okay, so we definitely want a different way out of this scenario. Okay, so here we go. Here's how we're going to use change of variables. This is a very clever trick I'm about to show you. I wish I'd thought of it on my own. I absolutely did not. Somebody showed this to me. Somebody probably showed it to them, etc. Everybody's copying off of everybody else for the good ideas. So here's the good idea. Very clever that you know, again, you don't expect that you would have thought of this on your own. Oh, whoops, wrong color. Take your given edge vectors that represent your parallelepiped and make those the columns. As I've done here, make those the columns of a matrix. Right? Here, let me highlight this more carefully. Make those the columns of a matrix. Use that matrix to define your linear transformation. And that's going to be super convenient as a change of variables function, as it turns out. So again, I'm going to show you why this works out so well momentarily. But the big trick to remember, the edge vectors defining the parallelepiped, make those the columns of your matrix. Okay, so who cares? Why is this a good thing? Let's see here. Let's erase all that. Let's think about the unit cube over here now, for no apparent reason. There's the unit cube. I want to think about what is the image of the unit cube. Okay. Well, the way we're going to understand the image of the unit cube is by looking at the edge vectors one at a time. Here, E1, for example, is my first edge vector of the unit cube. What happens when I plug in E1 into this brand new change of variables function that I just wrote down? Okay, well, I'm going to take that vector and I'm going to plug it into there to compute the image. Right, I'm plugging it into the linear transformation. You can see what's going to happen is I'm going to have to multiply A times that E1 edge vector. And what happens when you multiply A times E1? You get the first column of A, which by construction, by our clever sort of working it out in advance, we've already arranged to be the first edge of the parallelepiped. Right, so this is why we love this move. This is why this is an awesome move. The edge vectors of the unit cube, their images are the edge vectors of the parallelepiped. And then by linearity, and again, this is a linear algebra exercise. Y'all can fill in the blanks for yourself. That means that the image of the entire unit cube is the entire parallelepiped. And so as desired, right, we have a desirable little pullback domain over here, the cube. Its image is our nightmare domain over here, this parallelepiped. And so when I do my pullback, my original integral that I was asked to compute, this monstrosity here, yikes, will pull back to the much more desirable integral here on that unit cube to give me that integral. So no more fear of potentially 20 or 30 separate nightmarish iterated integrals. No problem. One single iterated integral 0 to 1, 0 to 1, 0 to 1, right? Everybody's favorite domain for triple integral. Because of change of variables. Okay, real slick move. Now, do make sure to remember, of course, right, that when you do this, you have to include your stretching factor. Your stretching factor is your absolute value of your Jacobian determinant. Don't forget our little preliminary theorem here. When you use a matrix to define a linear transformation, then the derivative matrix is the exact same matrix. So all I have to do to take my derivative of my take my derivative matrix of my transformation is to just take the determinant of the original matrix that I constructed from the given columns. Okay. Yes?
What's the 0 u plus 1 v plus 5?
Oh, yeah. So I have to plug in. I have to write down a formula for what z is. Right? And you got to keep in mind, z is one of the coordinates of the output. It's the third coordinate of the output. So it's going to be the third coordinate of that, which means it's going to be the third coordinate of what I get when I multiply a times uvw. And when you multiply a times uvw, that third coordinate is going to come, the coefficients will come from the third row, and thus will be that. Is that cool?
Yeah, thank you.
Okay. All right. Okay, so that's a very slick example there, and we move along now. That finishes what I'm going to call the change of variables stuff. Awkwardly, though, this book includes like a whole bunch of stuff all in the same book section. This happens in several places. I think we had one some time ago. I've already forgotten which one it was, but this is another one of these sections that's just massive and really should have been 2 book sections, and I would make a case for 3 myself. Anyway, so we're technically still in the same section, but this is really kind of a new topic. Okay, so the new topic is called integrals in a coordinate system, and the big idea here is just remember that a coordinate system is a function, right? In particular, polar coordinates is a function that takes r's and thetas and turns them into x's and y's as per certain formulas. And now I make the modest observation. This has all the earmarks of a change of variables function, right? It takes 2 inputs and gives you 2 outputs. Right? Now, again, you can think of polar coordinates as being, oh, that's just kind of a different geometry inside of the xy plane. You can think of it that way, but let's not, because it's really useful to think of it as a function so that we can say, hey, that's going to be my change of variables function. And we're going to see a bunch of examples where specifically this function, that function given by these formulas is going to be an awesome change of variables function. We're going to use it a bunch of times. Now, since we're going to use it a bunch of times, rather than compute our stretching factor every single time we go through that process, how about this? Let's compute it once and just remember it. And then we don't have to compute it every time. Right? We can just cite something we've done before. So I'm going to, again, leave the algebra of this as an exercise. It'll take you about a minute to 2 minutes. It's really easy. Just write down the appropriate partials to make your derivative matrix. Take the determinant to get the Jacobian determinant. And it's going to require a little simplifying, but the nice punchline is the Jacobian determinant is just R. The bad news, of course, is that Jacobian determinant is not the stretching factor. The stretching factor requires taking the absolute value. And, okay, so nobody likes absolute values. You can't do integrals with absolute values left in your expression. It sure would be nice if we could avoid these absolute values, but they are part of the formula. So here's the little hack that we're going to do to work our way around the absolute values, and that is we're going to voluntarily, of our own free will, choose to no longer allow negative values of R. Now, we don't have to, right? We don't have to. There's no reason that we have to. But if we do, right, if we restrict our focus just to, non-negative values of R only, and if we promise never to go over to where R is negative, well, now absolute value of R is no problem. Now absolute value of R is just R. And that's the payoff. Right, so y'all will recall back in Chapter 1 when we were talking about polar coordinates, I made the observation that, look, you can't just go around imposing rules for no reason. And at the time, we had no reason to restrict allowable values of R. Right? But now we have a pretty good reason. Now I see that if I make this choice, and again, not that I have to, but if I choose to do that, then I get the added benefit of avoiding absolute values. Is everybody on board? Okay. All right. Okay, so with that noted, we can do the same thing with cylindrical. It's a change of variables function, this time three-dimensional change of variables. I can compute the Jacobian determinant. Not surprisingly, we get the same answer as we got from polar. The Jacobian determinant is R. Again, we have to worry about absolute values, and we don't like that. And so again, we're going to choose. Again, not that we have to, but we're going to sacrifice the option of using negative R, which let's be honest, we didn't really like negative R values anyway, right? So we're going to trade this thing that we don't like, namely negative values of R, for the benefit of being able to get rid of those absolute values again. Same deal, practically identical to polar. Okay. Okay, and then on to spherical. And again, it's a change of variables function. And again, you can compute the Jacobian determinant. This one is a little bit more tedious. It's not horrible. This is more of a 5-minute calculation instead of a 2-minute calculation. There's a bunch of trig involved. It's a healthy exercise. I encourage you to give it a try. It's not that big a deal. You are going to have to be careful and organized. Right? This, too, is a healthy exercise. Right? And once you've done several Pythagorean identity simplifications, rho squared sine phi is your answer. Okay, now, again, we find ourselves having to worry about absolute values, right? This is not good enough. I have to say absolute value. Here's where a lot of students mess up. A lot of students think, oh, you know what, spherical, it's basically polar, it's a tweak on polar, and rho is kind of like R. And so, since here we just required R to be positive, and we got rid of the absolute values, surely here we could just promise rho to always be selected to be positive. And the absolute values, some students would think would just disappear. And of course they don't. Not even close. Look at what happens here. If you just promise to make rho positive, oh, come on, here we go. You promise to make rho positive so that that's positive. Well, so what? It was going to get squared anyway. That factor was positive no matter what. Making promises about rho doesn't accomplish a thing. It just doesn't. Right? So don't make that mistake. Don't think that, oh yeah, rho is kind of like R. It's really not. Right? The analogous argument here is to say, look, this is what I need to worry about. I need to worry about sine phi. I need to figure out how I can restrict my choices of phi to make sure that sine phi is always positive. And how do we do that? Well, again, just a little bit of trig, but as long as I make sure that I choose my phi between 0 and pi, then sine phi will be positive. Rho squared, of course, is never negative, and therefore that product will never be negative and the absolute values disappear. Okay, so again, good news, good news. These are the only values of phi I really liked in the first place. So as long as I promise to use only my favorite values of phi, then I get the benefit of not having to worry about absolute values. All right. There we go. Okay, so let's do one. Here is our question. We're going to look at an integral defined on this domain. Here's our integral. And I'm going to argue that this is an undesirable domain. It's undesirable. I mean, I've seen worse, but if you slice this up in the usual rectangular fashion and you look at a, for example, an x slice, and you look at the range of values of y, you can see that because of that being on the circle, your upper bound for y is going to be a square root. And this integral that results, that's pretty inconvenient. You can do it. Trig substitutions, clever integration by parts. This can be done. It's effort, though, and it's not desirable, and you really don't want to. So, how can we avoid that? We're going to avoid it, there we go, by using polar coordinates, as previously discussed. And all I have to do is figure out what is this domain over here. I'm going to currently leave as a question mark. What is the domain in our theta world whose image is exactly that quarter disk? Right? Because this is what I'm given. Right? That's what I sort of have to work with. I need to find the pullback domain for that quarter disk. How are we doing? Is everybody on board so far? Yeah. Okay. All right. I claim it's this rectangle. Let me try to argue for you that this is the pullback domain. Let's take this one edge at a time. I'm going to start with, how about I start with this edge right here. What happens? I look at this edge. You can see this is on the r-axis, so theta is equal to 0 is the starting point, and then theta equals 0 for the whole time, right? And then we're going to move along the r-axis until we get to where r equals 1. So theta equals 0, start at r equals 0, end at r equals 1. Well, that's exactly this edge right there. Right? That's just how polar coordinates work. Okay, next, let's look at this edge right there. That edge, it has r equals 1 for the entire edge. And we start where theta is 0, and we end where theta is pi over 2. Okay, how does that look like in the xy plane? Well, we stay on r equals 1, starting where theta is equal to 0, and ending where theta is pi over 2. So that gives us that edge. And you keep working your way around. This goes to that. And this wrong color. This entire edge here, this is a little bit of a tricky one. This entire edge, on the theta axis, this entire edge is where r is 0. The whole edge is where r equals 0. That means that whole edge is squeezed down to just the origin, where, of course, r equals 0. Is that cool? So check it out. We win, right? So this domain here has as its image the given domain that we started with. And now we are perfectly set up to do a pullback. We have our new pullback domain, and so it's just kind of a matter of writing it down. Let's see here. Yeah, right. So x squared plus y squared. I got to figure out how to write that in polar coordinates. Lucky break, it's an easy one. Now, you could have plugged in x equals r cosine theta, y equals r sine theta, and multiply it out, Pythagorean identity, right? You can, or you can also just remember that that's one of our path formulas. X squared plus y squared is r squared. Okay. Don't forget the stretching factor. Really easy to forget that. The stretching factor, of course, being as previously computed, just r. Our new domain is this rectangle, as previously argued. That rectangle, of course, is pretty awesome in terms of bounds. It's just that. Everybody loves rectangles. And we're in business. And by the way, look how easy this integral has become, right? I mean, our initially, this was going to be a bummer of an integral, but on this new domain, it's just about as easy as you could hope for, right? Constant bounds, no weird functions, no square roots. Works out great. Everybody all right with that? Okay. All right. Now, I went quickly through this part where I took my domain and just kind of listed the bounds like this. Let me slow that down real quick. I know you believe it. I know it. I mean, it's pretty straightforward slicing process. But just to recognize what the process is, I've got to understand what my theta slices look like. Right? I've got to think about the first and last slices, those giving my theta bounds. And then I've got to think about on a particular theta slice, I've got to think about first and last for R. And of course, the first for R is 0, and the last for R is 1. So that was the process. Right? Now, notice that every part of that process boils down to understanding what the theta slices look like, and then thinking about the corresponding values of R on a given theta slice. So if you understand the slices, then that gives you what you need. Now, why do I want to make that distinction? Well, I want to make that distinction because the good news is these theta slices, you can see them in XY space. Each one of these slices, it just represents a constant value of theta. Like this one here, this slice down here, that's just theta equals 0. This slice right here, that's just theta equals some slightly larger value. Each one of those theta slices then, just in the XY world, looks something like this. So here's the clever insight then. If all you need from your pullback domain, if all you need is to understand the R and theta bounds, and if the R and theta bounds are going to be determined entirely from the slices, and if we know what the slices look like over here, then we can just as well do our slicing over here in the XY world. I can see all the slices. And you don't have to draw the pullback domain and slice it up in that new world. Let me show you an example. This is the exact same example that we just did. We already have the answer. We know what the answer is, right? But let's think through the sort of the slicing process. Sure, I can imagine that I'm looking at that theta slice right there, but I can see it right here just as well. Right? I can see from thinking about what these theta slices look like, that this first theta slice is clearly going to be where theta is 0. And I can, again, just as easily as looking at that as being my last theta slice, I can just as easily see that theta slice over here in XY world. That's pointing in the pi over 2 direction. And so my last theta slice is pi over 2. So, nice punchline. I don't even need to draw my pullback. The only reason I would need to draw it is to, again, for the purpose of slicing it, and I can slice it over here. Everybody buy it? Okay. So, going through that same process, going through that same process, again, we write down our plug-in, right? And we don't forget your stretching factor. And now let's think about the slicing. And okay, well, theta goes from 0 to pi over 2. And then for a given theta slice, for a given value of theta, let me switch colors again. For a given value of theta, like that. Notice that R starts at that point where R is pretty clearly 0. Right? And R is going to end at that point, which is on this curve, which has that equation. Solve for R, and you get R equals 1. So we don't need the picture on the left at all. Now, it remains. So I don't overinterpret here. I'm not saying we're not doing a pullback. We absolutely are doing a pullback. This is still change of variables. I just don't have to draw. I can spare myself the artistic effort of redrawing the pullback domain, and everything you need from it you can see right over here in the XY world. So this is a really convenient trick. This is I would say, when we make the transition from thinking of this as using polar coordinates as a change of variables function, and instead start to transition to the terminology, we're doing the integral in polar coordinates. It's really just a shorthand terminology for doing a pullback through a change of variables function using polar coordinates. Okay. All right, so let's see another example. Here I'm going to completely abandon the idea of drawing the pullback. No pullback drawn. It's still there. We're still doing it. It's still a change of variables, of course. Okay, well, let's see here. Plugging in, that is pretty clearly R. Don't forget your stretching factor. So your dA is RdRd theta, as previously discussed. Now let's think about the bounds. And the bounds, well, theta kind of goes all the way around. Right? Theta, for example, you could view it as starting right there, where theta is equal to 0. And rotating all the way around as theta slices do, then ending at 2 pi. And you could draw yourself a pullback domain and slice it up in the usual way if you just want the artistic challenge, right? But might as well just do it the easy way, like this. Okay, now let's focus on a given theta slice. So some value of theta between those extremes. There's a theta slice. Notice that we are going to start at the origin, where, of course, R is 0. And we're going to end at that point on that curve, which is the unit circle, which has the equation R equals 1, where R is 1. And there you go. There's your bounds. No pullback needs to be visualized. How are we doing? Is everybody okay with this example? Now, of course, all the rest of the details, you got to carry it all through a bunch of calculations, blah, blah, blah. But that's the big idea. Okay. All right. Several more examples to follow. That clock is wrong. Here, let me just real quick. I just want to see what time it is. Thank you. Okay, appreciate it. So there's a couple of tips and tricks I think are really useful. Good news, even though you do have 2 different choices for the order, in practically all cases, you should use this order. So I would suggest don't even think about it. Don't even consider the possibility of doing d theta dr. I've never seen what I will call naturally occurring example where d theta dr was a better choice. And it's been a lot of years, and I've done a lot of integrals in polar coordinates. And dr d theta is always, in my experience, I mean, don't get me wrong. I have, when I was in a weird mood one day, I contrived a very strange counterexample where, d theta dr works better. But it was weird. It was extremely unnatural. I've never seen it arise, organically, they say. So just always do the differentials in that order. Secondly, I advise that when you write down dr d theta, always write R before you write down the drd theta. Always write them down together. Because you think about it, when you're doing an integral in polar coordinates, it does remain, let's see, well, I guess I'll do it like this. It does remain that the only reason you're getting an integral in the r theta plane is because you're pulling back from the xy plane, which means you are doing a change of variables, which means you're going to need that r every time. You will never have a need to write down just drd theta. So the reason this matters, and I think you should write them down together, is because it is surprisingly common to forget that r. Give me 2 seconds. Super easy to accidentally forget the r. And what happens is you write down the drd theta as your little sort of your recognition that that's the end of the expression, and then you start thinking about the geometry of the slices and all of that business, and sometimes having to find the polar equations for certain curves. And then when you get all that done, you feel like you finished, and you just forget. And if you didn't put it down there in the first place, you might never remember to go back and do it. Now, this is I haven't forgotten you. This is a big deal because of the following fact. And that is, this R, it's the stretching factor. It's the big multivariable calculus idea of change of variables. It's super important, right? In terms of, looking at one of these kinds of questions and, a valid solution to the problem. This is one of the more sophisticated, mathematically meaningful parts of the solution. So it's worth a lot of points, right? And again, it makes me cry a little bit every time I see a student's paper where they just wrote down the drd theta. And I know what happened. I know they got distracted and that they almost certainly would have remembered except they forgot. But I have to grade based on what's written on the page, and then I can't give them the points, right? So think of it this way. Think of it in a glass half full, not a glass half empty kind of sense. If you just follow this advice and just write down r drd theta all together, that's free points. That's money. That's it could be as much as 5 points. That one little thing, and don't leave the money on the table. Get that money fast as you can. Does that make sense to everybody? So strategically very important. I'm sorry, go ahead.
Yeah, you're good. So this might be a really dumb question.
It's okay.
There's no pullback. You have to account for the stretch factor. Could you go into the difference here? So there is a change of variables.
Yeah.
R, but there's no pullback.
So I hear where you're coming from. Let me correct that a little bit. It's not that there isn't a pullback. There absolutely is. It's just that I don't need to draw it. Right? So it's there. It's part of what we're doing. It's part of the argument that we're making, but we don't need to draw it because everything that I would have needed, right, from the pullback, I don't need to deduce from having drawn it. I can get that information just by looking at my original domain. So it is a change of variables. It is a pullback. There is a stretching factor because of the change of variables. That's all true, right? It's just that artistically, you just don't need to do that.
Maybe I'm just struggling to understand where you do need to just draw the
or when you would need to draw the pullback?
Yeah.
So in cases where you're using a change of variables function that's not polar coordinates, right? That's not one of our standard go-to things, right? Where we have this fantastically convenient experience of, I know what theta equals 0 looks like because I've done a bazillion examples in polar coordinates, as you have, right?
You can see it in the XY plane.
Yeah, exactly.
Okay.
So the reason that we can see this easily is because we have all of that extensive experience with polar coordinates, right? And so if you're doing like a different example where you made up a brand new change of variables function, you have no such experience, and therefore you have to draw the pullback.
Awesome.
Yeah.
Thank you.
Cool. Okay. So yeah, second trick. Big one. Make sure to always write down r drd theta all at once. Get those points in the bank, and then go off and think about other things. After you've already got that. established. So let's see here then. Last little trick is really just a repeat. We already know this process when you're trying to find your bounds. We know they come from understanding where the endpoints are. The endpoints are on certain curves that have certain equations that you can solve to find your bounds. So let's do some more examples. Here's one. This is kind of a weird one. It looks like an easy integral because the domain is this, which doesn't look so bad. It's called an annulus. And it's tempting to say, and a lot of people would do the following, it's tempting to say that I can just take an integral on the big disk and then subtract the integral on the smaller disk, right? Blue minus purple would give us the annulus that we're actually interested in. So, yeah, that doesn't work. Doesn't work at all because of what the integrand is. Our integrand here, our integrand is undefined at the origin. Right? It has a nasty singularity at the origin. It approaches infinity, right, at the origin. And now you might be thinking to yourselves, oh yeah, this reminds me of improper integrals from single variable calculus, right? You remember sometimes you can work that out with an improper integral. Turns out improper integrals in a multivariable context is a whole different deal. It's really not analogous. Things get weird. And that's not something that we're going to be able to address in this class. So you can't define these integrals. So this is dead in the water. So tempting, but doesn't work. So we then say, all right, well, fine, I'll just slice it up in rectangular coordinates. But notice if you slice it up in rectangular coordinates, the first thing that happens is you have to stop there because you're side-swiping a face, thus leaving you with kind of a top piece and kind of a bottom piece. After which you then they sort of rejoin, and then you get this side piece. In grand total, you're going to have 4 separate integrals here. And furthermore, these are all 4 nasty integrals because the bounds in rectangular coordinates, these bounds come from circles, which are going to involve square roots. So you're going to have ugly integrals. Right? So this is a terrible way to solve the problem. Right there. Okay, so let's use polar coordinates, and it's just super convenient. Apparently we're going all the way around. Theta goes from 0 to 2 pi, easy observation. And then for a given value of theta, r starts at that point, which is on that curve, which has that equation. Solve for r, you get your lower bound of 1. And r is going to end at that point, which is on this curve, which has that equation in which you solve for r, and your upper bound is 2. That is super easy. Everybody see how that works? Okay. So nothing to it. Okay, let's see. We have a minute left. Okay, let me hit some highlights on this one. Our domain is this shaded region, which you'll notice is part of one disk that's outside of another disk. We're going to need to look at our theta bounds. This is what a theta slice looks like. Our starting theta bound then is going to come from that point, this point. Now you can look at the curves that it's on and play algebraic games, but you can also notice that these 2 edges are radii of this circle of radius 1, so I know those edges are 1, and this is a radius of that circle that's also has radius 1. So I have an equilateral triangle, and that very conveniently tells me that my lower bound for theta is negative pi over 3. So just be on the lookout for every so often you get lucky with the geometry. You capitalize on the freebies when you find them. Okay. Everything else in this example is pretty straightforward, I think. So I'm going to declare us done with this page, and we'll pick up here on Friday. Y'all have a good rest of your day. See you later. Don't forget about attendance, by the way, if you came in after I did it.